So good morning, everybody. This talk is about improving the performance per area factor of RISC-V based multi-core systems. And I'm Tobias Strauch, and I'm working for Adaptix in Munich. So we'll talk about Slow Retiming, system hyperpipelining, here in particular about performance balancing and performance per area factor. And then I would like to introduce two projects. So let's talk about Slow Retiming. This is a very simplified view of a digital design. We have combination logic and registers, and let's forget about the inputs and outputs. If you apply Slow Retiming, you add the same number of registers into each pass. Then you generate C individual copies of the design. A color here is a design state, so an individual design. So you have here 3 designs running. And now you might say, wait a minute, that's classical pipelining. Well, if you apply Slow Retiming on a CPU, here we have an unrolled version of the simplified view with fetch, decode, and execute state. You would have something like this, that you have multiple threads running on the original CPU. So Slow Retiming is known since the 60s. Processors based on Slow Retiming are called barrel processors. Mr. Leiserson mentioned Slow Retiming first in his paper. There was a Berkeley summer class in 2001 about that, and the Berkeley guys released a paper about Slow Retiming on FPGAs on lookup table level. But I guess millions of engineers have had these ideas. So even I had this idea, and I did write my diploma thesis about this. And my first job was at LSI Logic in Milpitas, supporting RISC processors, and I tried Slow Retiming on gate level, but was not very successful. And then I quit my job and started a company basically doing timing estimations on RTL code modification, and these kind of things inspired by the upcoming physical synthesis aspects and so on. And in 2010, Slow Retiming came up again, and I said, hey, why not using my tools and apply Slow Retiming on RTL? And so I have 2 examples on open cores, the AVR core and the OpenRISC core, where I applied automatically Slow Retiming on it. And I continued research on that, Slow Retiming and safety critical designs, and so on. Slow Retiming designs generate a lot of shift registers. So I thought, hey, replacing these shift registers with memories would be actually very helpful. And it turned out that it's also very helpful on system level. So I call the whole thing system hyperpipelining. So you replace the original registers with memories, and you add a thread controller. And the first aspect would clearly that you can now run more threads than with Slow Retiming, right? So system hyperpipelining is based on Slow Retiming. It replaces the original register with memories with a memory depth of D, and it adds thread stalling and therefore thread bypassing features. And it adds a cycle accurate performance balancing. And mentioned that shift registers, they can be now merged into the memories with a late read or an early write mechanism. Okay, so let's compare the different scenarios. We have the original design here on the left. And when you apply Slow Retiming, you have a fixed thread order. You cannot change that. The first aspect is that with system hyperpipelining, you can run more threads if you want, but you can easily switch between the minimum threads and the maximum number of threads. But more importantly, you can insert threads, you can stall them, you can kill them. And with a priority scheme, you can even have a predictive runtime of specific threads. You can start them synchronously, and you can execute them in parallel. So you can easily generate dynamic length instruction words, like you can group them. And in the next 2 slides, I would like to show 2 further improvements to run at least one thread faster and to have a reduced minimum number of threads to achieve the maximum system performance. Because you might not want to run 16 threads, you might only want to run 4 threads and achieve the maximum possible system performance with that. So one method I call deep pipelining. The idea is to run one thread in beast mode and gives a complete pipeline to one thread. But then you need to quickly decode the instruction dependency. And one trick would be to use a least significant bit to tell the thread controller that the next instruction can be executed immediately. If not, the thread controller gives this time slot to another thread. So you implement a kind of instruction, least significant bit sniffing. You enhance the program memory read, and you still have to consider stall and flash signals. I wasn't able to run it back-to-back instruction, but it works with every second instruction, and you can turn on and off this method on the fly. The second method is extended pipelining. I haven't found a right word for that, but in a paper about that with frequency over scaling, the idea is that you adjust your clock period to the current instructions you're executing. So the first thing you detect potential multi-cycle paths in your design, the multiplier, for example. Then you insert less registers into the path. You see if one of these multi-cycle instructions is actually executed. And in this case, you simply re-execute that thread. So these are two methods to improve system hyper-pipelining on top of the original modifications I told you. So the performance per area factor. The black line shows the classical improvement. You have 3 cores, you have 3 times the performance, so a simplified view. And the green line shows that with increasing design copies, the overall system performance decreases. But in this case, it all comes with a very low FPGA slice utilization overhead. So, for example, in this case here, I hope I press the right button. For example, in this case, you have with 14% more utilization, you have 220 or overall 320% performance compared to the original design. And the slide also shows the 2 improvements I was talking about. For example, if you have C equal 4 and you say we have 1 multi-cycle pass through the multiplier, you can run 3 threads, all of them a little bit faster than the original one. And if you turn one thread into beast mode, you can run it at 150%, and you only need to use 2 more threads to achieve maximum system performance. But you can use up to 16 threads in case you use an FPGA with D equals 16. Okay, so the numbers are based on the CH-Stone test cases. So let's talk about the system level. So far we talked about performance over area curve in the classical sense that we increase the frequency, and system hyper-pipelining is also about system level performance improvements. And for that, I created 2 projects. One is a micro-RISC project, and one is a mini-RISC project. So the VScale is Berkeley's Verilog version of the IM RISC-V, and it runs at 80 megahertz and needs an asynchronous interface to an DDR controller, here shown in yellow. on the left-hand side. And on the right-hand side, you see a system hyperpipeline version that runs at 250 megahertz. And it does not need a synchronous bridge anymore, which is, for example, one of the system-level impacts. It's based on the subset of the IM because it does not use fetch or system instructions. It might make sense. Many people say that their core is compliant to the IM instruction, but they don't use fetch and system information instructions. So it might make sense to call that subset, gives that subset a special naming. The next aspect is that an individual thread can handle an interrupt, so you need less stack handling, which is another system-level aspect. But here I'm focusing on virtual peripherals, so instead of having a fixed or synthesizable set of peripherals, I use virtual peripherals. For that, the thread controller is enhanced with an event handler, which is more or less a complex timer. So it fits on the RT board, and excuse me, it's still compatible to any kind of language because the thread controller is accessible like a peripheral, but you can use the Arduino environment. You just implement the virtual peripheral as a software, as a code, and you set it up, and then you can use it. So this demo is not about Arduino. This demo is how to run timing-critical software peripherals based on a highly dynamic system hyperpipeline core. So I want to show the responsiveness of this multi-threading approach. The next project is based on the low risk, and Wei was so kind to send me his slides, so I don't need to redraw that. It's his personal view, so okay, everybody knows the Low Risk Project. Thanks again, Wei. And I have it working on the uneased version, but I kind of over-engineered it. I apply Slow Retiming on the Rocket chip, on the Rocket core, and system hyperpipelining only on a subsection to run bare metal code. But that's really not sure if I'm going to release that. So as soon as the ASIC version is out, I will apply system hyperpipelining on the Rocket core, which is a 5 seconds approach because I have a tool for that. So you can, instead of having a multi-core version, you have now a system hyperpipelining core, and instead of having multiple minions or pulpinos, you have a system hyperpipeline microcontroller. And the next system level aspect is that instead of having a multiplexer-based system bus, which is kind of blocking, or a multi-layer bus, which is complex, system hyperpipelining has an impact on the system bus because it uses, I can use the system bus quite naturally in a time-sliced fashion, so it's less blocking. So it will be a one-to-one replacement of the original one, so the same software can run, but it will be smaller, it will be faster, and a higher system throughput. That's the whole idea, and you can then add additional improvements. So finally, this is a programming model. It's very simple for this. You can easily program fork join operations, and you can add OpenMP here. I have estimated ASIC numbers in one of my papers. The hyperpipelining methodology of Altera looks very promising. Yet again, I would like to say that FPGAs need more memories on chip. There's work ongoing to reduce the power consumption of system hyperpipelining cores, and the projects will be released in PDVL, which is my main research focus. It's a language way better than Chisel and Bluespec Verilog. Sorry. But there's a compiler for that, so you can have a VScale and Verilog version. So these are the references, and I'm very happy if you talk to me, especially if you have access to ASIC technology, and if you want to try an ASIC version, I would be very happy to cooperate. Thank you so much.
Thanks, Tobias. Any questions?
Rishir Nikhil from BlueSpec. I don't think it's better, but anyway. You mentioned dynamic scheduling for the threads. You're scheduling the threads dynamically. How does that work?
The thread controller can assign a slot to individual threads on a cycle-by-cycle basis. So you can run 4 threads, 5 threads, 7, and you can adjust that cycle by cycle.
But on what basis? What's the policy of choosing what thread to?
Priority decoding. I mean, you have a queue where they all line up.
Yeah.
And if a thread leaves pipeline with a higher priority, it is re-entered first, and interrupts might have a higher priority. And and if they have the highest priority, they are not interruptible, so their runtime is predictive. If you have a minimum number of threads, for a minimum number of threads.